In this video, I'll explain how in problem set 4, you work out one of the problems. A full solution set is already posted for you. All right, here goes. So I've got this problem here. A ball rolling down a hill can be modeled using uniform or constant acceleration. Suppose the ball starts from rest at a position of 0 meters and moves along the positive x-axis, accelerating at 0.5 meters per second. Complete the data table. So a couple details. The acceleration is given to you, as is the initial velocity and the initial position. Those were stated 0 meters from rest with an acceleration. In the future, I'll expect you to be able to infer these highlighted quantities from a written description rather than giving them to you on the data table. Now, how does that acceleration affect the velocity? Start with velocity. So from 0 to 1 second, the velocity is going to increase. The way you can read the acceleration, 0.5 meters per second increase in the velocity for every second on the clock. That's what that second means. So 0 plus 0.5. Do it again and again, all the way down. This sets up for us a constant acceleration situation. Just FYI, it's going to look like this. A linear function with a slope equal to the acceleration. Now, what the heck is happening to the position of the object? We're going to fill that in just a moment. Let's go ahead and work this on the data table first. All right, so I start at a position of 0. Where will I be located 1 second later? So how am I going to do this? There's a couple of ways to go about it, but I'm going to encourage us to think about what we were doing previously with graphs. It looked like this. So here, I'll get rid of that for a moment. And I'm going to say, well, we're going to run out to some amount of time, up to some velocity, final, and this represents the displacement, or how far we've moved since 0 seconds. So our time here on this triangle is 1 second. And at the end of that 1 second, the velocity, according to my table, is 0.5 meters per second, right? That's this. Displacement is the area of that triangle. 1 times 0.5 times a half. One half base times height. Here, hang on. Base. 1 second times height, 0.5 meters per second. So let's see, what's half of a half? That's 1/4. There is another way to do this. Show you that other approach now. The other approach is to apply the idea of average velocity. So I'll do this in a different color this time. Average velocity says that if you take the initial velocity and the final velocity over some time period, add them together and divide by 2, that'll get you an average velocity. Multiply the average velocity times the time interval. So average velocity is 0 plus 0.5 over 2 times the amount of time. Half of a half again, back to 1/4. So either calculate using average velocity or the area of this velocity time triangle. Either one is good. I'm going to roll back to that other calculation, and I'm going to place that calculation next to where its result is. And let's calculate the next one. So now I'm going to go out to 2 seconds on the clock, where I have a velocity of 1 meter per second. You'll notice that I'm using these numbers here, 2 and 1. Okay. All right. 1/2, 2 seconds on the clock, and 1 meter per second. 1/2 times 2 times 1. Do the next one. One half times 3 times 1.5. 2.25 meters. I don't have that kind of math, just memorize that. I've calculated this before. I want you to continue the process all the way down, pause the video, finish your calculations, and then come back and we will check that you've got the right answers all the way down. Here are my answers to all the numbers on the table. After you've double checked that all the quantities match up with yours, let's take a look at the next part of this. So this data table that we just created, it's called a computational model because we spent a ton of time filling in a bunch of data. And a computational model is something that relies on tons of computation. That can be done by a human or by a computer, but the idea is to generate a ton of information. You could then graph it, but it doesn't directly answer a whole lot of questions. It describes general trends. So if I was to ask you what the ball's position was at 42 seconds, the model we've created so far, it would be really time consuming to answer that question, right? I'd have to carry out this data table all the way to 42 seconds. I guess I could skip to the 42nd row and just do that calculation. But the problem with that is, in order to calculate this final position here or some position way out further in the future, I needed to know a velocity here. The velocity we're talking about here is that 10. So without getting every row in between, let's work on how you can do that. So this equation here gives a person position as a function of time. We're not going to focus right now on where this equation comes from, but rather accepting it as true, we can use it to calculate future positions. Let's just double check that it works and confirm the position at 10 seconds. So here you go. Bring this down. Position is the initial position, 0, plus the initial velocity times the time on the clock, plus 1/2 times the acceleration times the time on the clock squared. You'll notice these first two terms, 0 and 0 times 10, they're zeroed out. So now we're going to do 1/2 times 0.5 times 10 squared. I get a position of 25 meters. So that checks out. Now let's actually answer the question. The position of this object at 42 seconds. Let's go ahead now and calculate 0.5 times 0.5 times 42 squared. I get 441 meters. So you can see now that that calculation, it's pretty straightforward. You don't need to memorize it, but you can use it to calculate future positions anytime in the future if what you know is the acceleration and the time that you want to calculate the value for. This is useful for calculating discrete or individual values. Okay, that does it for this video where I worked out the entire first page of problem set 4. Again, the full solutions are available in a PDF format for the rest of problem set 4 so that you can check your answers. Take care and good luck.